Master Manipal is proud to present its rover for University Rover Challenge 2022.
This year, the mechanical subsystem aimed to reinforce the robotic manipulator and make further improvements to our drive system. Our custom 6-wheel dependent suspension based on a 5-bar mechanism allows the rover to climb obstacles up to 0.6 meters and descend a vertical drop of 1 meter. The 5-bar mechanism is constrained by preloaded torsion springs, allowing optimal ground conformability. The suspension and antenna articulation enable the rover to fit the required 1.2 meter cube. The chassis comprises a compact tubular space frame structure serving as a mount for auxiliary rover modules. Our modular lightweight 3D printed wheels improve ease of assembly and are interchangeable with low pressure polyurethane balloon tires. The wheel assembly features a fully floating axle powered by multi-stage planetary gearboxes. Each prototype has been extensively tested based on strength and compliance. The 6DOF articulated robotic manipulator, fabricated using carbon fiber tubes, features two high-power encoded linear actuators. Backdrive is effectively prevented by a zero backlash 1:40 reduction worm drive in the swivel base, while shaft eccentricity is compensated for by an Oldham coupling, ensuring smooth power transmission. The end effector comprises a bevel gear differential and a lead screw base gripper that allows for precise interaction with the environment. For extreme retrieval and delivery task preparation, rover traversal has been tested at a dedicated site consisting of steep slopes, vertical drops and rocky fields. We have practiced carrying various payloads to specified locations and pulling objects attached to ropes, thereby testing the mission readiness of our rover.
The electronics and control subsystem focuses on operating the rover, integrating core electronics and embedded systems. Custom PCBs have been designed to optimally utilize the limited space available inside the chassis, thus reducing wiring and making rover maintenance easier. SolidWorks Electrical 3D has been used to simulate all real-time electrical wiring of the rover. ARM Cortex-based STM32 microcontrollers, acting as CAN nodes, are responsible for precise rover control. Each link of the robotic manipulator is attached with the PCB, which houses an IMU and the STM32, which connects the entire manipulator on a single CAN bus. Velocity kinematics integrated with our path planning algorithm has been utilized for end effector position control. Orientation values obtained from the IMUs is used as feedback in our PID algorithm to control the angular velocity of each joint. The 6-wheel skid steer is equipped with hill assist for maintaining the rover's position on uneven slopes. As an added measure of safety, a kill switch has been added for emergency stop of the rover. For the equipment servicing mission, a custom graphical user interface and an equipment servicing panel has helped us to practice opening and closing of latches and drawers, toggling of switches, operations of a joystick, inserting a rugged memory stick into a USB slot, and tightening Allen head fasteners. Our robotic arm is also capable of typing commands on a keyboard and inserting a cache container into a close-fitting drawer. To communicate between the rover and the base station, 5.1 GHz frequency bands are used. A combination of omnidirectional and directional antennas ensure a continuous communication link with the rover. The rover is capable of a non-line of sight communication link up to a distance of 1 km.
The air automation subsystem is responsible for designing the navigation stack for the autonomous mission. The computation is handled by NVIDIA Jetson DX2 and Jetson Nano. The control structure uses skid steer kinematics to compute PWM for the motors on an ESP32. The LiDAR and Z2 stereo camera generate point clouds. The visual odometry is fused with other sensor data using an extended Kalman filter. Our path planning algorithm is inspired by vector field histogram to avoid obstacles using a point cloud data. RTCM data from DGPS and IMU is used to traverse from one GPS coordinate to another. A custom search pattern algorithm has been developed to traverse the terrain along a geometric pattern to find Aruko markers and accurately estimate the position. The gate traversal algorithm uses the marker's pose to plan a triangular path parallel to the marker plane, avoiding the small space issue and traversing through the gate. Flashing green LEDs indicate the completion of the leg.
The life science subsystem has incorporated distinctive chemical assays to detect the presence of active biomarkers of extinct and extant life. Lead screw-based linear actuation assemblies are used for soil collection. 3 separate augers have been implemented to prevent cross-contamination between samples. Peristaltic pumps are utilized for delivering chemicals through the analysis compartment. This year, we have implemented a water bath powered by a magnetic induction heater to perform the DNS assay for carbohydrate detection. We have tests for detecting the enzymatic activity of soil, Bradford test for proteins, and HCl test for carbohydrates. Our sensor suite houses an optical microscope for comprehensive soil and rock analysis by studying the microscopic textures, patterns, and crystal structures. A total of 8 sensors have been implemented to detect volatile organic compounds, ozone, CO2, humidity, soil moisture content, electrical conductivity, and temperature. The spectral sensor-generated peaks are analyzed to determine the soil's chemical composition. A custom rock database has been formulated to efficiently identify and classify rocks present at the testing sites.